Welcome to our countdown of 10 true facts you won't believe. Get ready to have your mind blown as we dive into the strange, surprising, and downright unbelievable realities of our world.
The phenomenon of cold welding occurs when two clean, flat surfaces of metal come into contact in a vacuum or space environment, causing them to fuse together permanently. This occurs because, in the absence of an oxidized or contaminated layer, like dirt or oil that typically exists on Earth, the atoms of each metal surface do not know they belong to separate objects. Instead, they recognize the other surface as an extension of their own structure. This results in the formation of a single, continuous piece of metal, as if they were originally forged as one. In space, the conditions are ideal for cold welding because of the vacuum environment, which eliminates the protective oxide layers that form on metals under Earth's atmospheric conditions. On Earth, these oxide layers and impurities generally prevent atoms from bonding when two metal surfaces come into contact. However, in the vacuum of space, these barriers are absent, and when two metals meet with sufficient force or contact area, their atoms can interdiffuse, creating a strong bond. This phenomenon has implications for engineering and the design of spacecraft and satellites. Engineers take precautions to prevent unintended cold welding, such as using coatings, lubricants, or non-metallic materials to separate metal components. Cold welding can cause problems in mechanical systems with moving parts like joints, hinges, or bearings, as components could seize up and become inoperable. At the same time, cold welding can also be harnessed for intentional purposes, such as repairing or constructing structures in space without requiring heat or additional materials. Interestingly, cold welding is a purely physical process and does not rely on any additional energy input like heat, electricity, or pressure beyond the initial contact force. This makes it a fascinating example of how the behavior of materials can differ dramatically depending on environmental conditions, highlighting the unique challenges and opportunities of working in space environments.
The Sun, a vast sphere of glowing plasma, dominates the solar system by comprising 99.86% of its total mass. This staggering figure highlights its immense gravitational influence, which governs the orbits of planets, moons, asteroids, comets, and other celestial objects. With a mass approximately 330,000 times that of Earth, and a volume capable of holding over 1.3 million Earths, the Sun is the central anchor of the solar system, ensuring its stability and continuity. The Sun's massive composition primarily consists of hydrogen, about 74% by mass, and helium, approximately 24%, with trace amounts of heavier elements like oxygen, carbon, neon, and iron. These elements exist in a plasma state due to the extreme temperatures and pressures at its core, where nuclear fusion occurs. This fusion process converts hydrogen into helium, releasing vast amounts of energy that radiate outward as sunlight. This energy sustains life on Earth and drives the climate, weather, and ecosystems. Its gravitational pull is also crucial in maintaining the orbits of the planets. Without its overwhelming mass and corresponding gravitational force, the solar system's delicate balance would collapse, and celestial bodies would drift into space. The Sun's mass also contributes to phenomena such as tidal forces and the shaping of planetary atmospheres. For instance, the solar wind, a stream of charged particles emitted by the Sun, interacts with planetary magnetic fields and atmospheres, influencing auroras and geomagnetic storms. The Sun's dominance isn't merely physical, its mass defines the solar system's boundaries, extending even beyond the heliosphere to the distant Oort cloud. Despite its massiveness, the Sun is considered a medium-sized star, a G-type main sequence star, and its life cycle is expected to span about 10 billion years. Currently, at roughly 4.6 billion years old, it is in its middle age, continuing to fuel the solar system with its vast reservoir of energy.
Uranus, the seventh planet from the Sun, presents fascinating extremes when it comes to its rotation and orbital characteristics. A day on Uranus lasts about 17 hours, which is the time it takes for the planet to complete one full rotation on its axis. However, its year lasts 84 Earth years, the time it takes to complete one orbit around the Sun. These measurements reveal striking contrast between Uranus's day-night cycle and its seasons. A short day. 17 hours. Uranus rotates relatively quickly for a planet of its size, completing a full spin on its axis in just 17 hours and 14 minutes. However, this rotation is unusual because of the planet's extreme axial tilt of about 98 degrees. Unlike other planets, which spin more or less upright relative to their orbital planes, Uranus essentially rotates on its side. This makes its rotation retrograde, meaning it spins in the opposite direction to most planets like Earth or Mars. As a result of this tilt, each pole alternates between experiencing 42 years of continuous daylight, followed by 42 years of darkness during Uranus's orbit around the Sun. This unique orientation gives Uranus some of the most extreme seasonal changes in the solar system, even though the day itself is relatively short. A long year, 84 Earth years. While Uranus spins quickly on its axis, it moves more slowly along its orbit due to its distance from the Sun, an average of about 2.9 billion kilometers, or 1.8 billion miles. Its vast orbital path means it takes 84 Earth years to complete a single trip around the Sun. For perspective, this means a single Uranian season lasts about 21 Earth years, with each of the 4 seasons stretching over decades. The combined effect of day and year. The combination of a short day and a long year creates unusual dynamics on Uranus. For much of its orbit, especially near the solstices, one hemisphere experiences constant sunlight or darkness, depending on its orientation to the Sun. Near the equinoxes, when the Sun is aligned with the equator, Uranus experiences a more Earth-like day-night cycle, albeit with each day lasting only 17 hours. These factors make Uranus a fascinating study in planetary science. Its rapid rotation, extreme axial tilt and long orbit contribute to its unique climatic and observational characteristics. These features also influence its atmosphere, which is composed mostly of hydrogen, helium and methane, and result in dynamic weather patterns, including massive storms and high-speed winds, despite its frigid temperatures.
Titan, the largest moon of Saturn, is one of the most intriguing bodies in the solar system due to its thick atmosphere and surface features resembling Earth's hydrological cycle. With a diameter of about 5,150 kilometers, it is larger than Mercury and the second largest moon after Jupiter's Ganymede. Titan's atmosphere is dense and predominantly composed of nitrogen, about 98%, with small amounts of methane and other hydrocarbons. This nitrogen-rich atmosphere, the only one of its kind among moons, creates a hazy orange appearance due to the presence of complex organic molecules called tholins, formed by interactions between sunlight and atmospheric methane. The most fascinating aspect of Titan is its methane-based hydrological cycle, which is analogous to Earth's water cycle. Instead of water, Titan has rivers, lakes and seas of liquid methane and ethane. These hydrocarbon liquids are stable on Titan's frigid surface, where temperatures average around -179 degrees Celsius or -290 degrees Fahrenheit. Titan's largest seas, such as Kraken Mare and Ligeia Mare, are located near its poles and can span hundreds of kilometers. Methane rain falls from its thick clouds, replenishing these bodies of liquid in a process similar to the rain and river systems on Earth. The surface of Titan is a mix of icy terrain, sand dunes and liquid reservoirs, sculpted over time by erosion, tectonic activity and cryovolcanism. Beneath its surface, scientists believe Titan may harbour a subsurface ocean of water mixed with ammonia, raising tantalizing possibilities about the moon's potential for hosting life. NASA's Cassini spacecraft, along with the Huygens probe that landed on Titan in 2005, has provided detailed observations of its atmosphere, weather patterns and geology, offering a glimpse into a world both alien and familiar. The presence of organic molecules and an active climate system makes Titan a prime target for future exploration. NASA's upcoming Dragonfly mission, set to launch in 2027, aims to explore Titan's surface using a rotorcraft lander. This mission will investigate the Moon's chemistry and habitability, potentially revolutionizing our understanding of life in the universe.
The discovery of an enormous cloud of alcohol in space is a testament to the complexity and abundance of organic molecules in the cosmos. This giant cloud, formerly known as Sagittarius B2, is located near the center of the Milky Way, about 390 light-years from the supermassive black hole Sagittarius A*. It is a vast molecular cloud spanning about 150 light-years, making it one of the largest known repositories of organic molecules in our galaxy. Sagittarius B2 is composed of a rich mix of gases, including ethyl alcohol or ethanol, the same kind of alcohol found in alcoholic beverages. Scientists estimate that the cloud contains enough ethanol to produce about 400 trillion pints of beer. However, the alcohol isn't in a form that's drinkable or harvestable. It exists as a vapor mixed with other complex and often toxic compounds. The temperatures and pressures in this region make it a fascinating laboratory for studying the chemistry of organic molecules under extreme conditions. This molecular cloud is a hotbed of prebiotic chemistry containing more than 50 identified complex molecules, including amino acids and other building blocks of life. The abundance of organic molecules suggests that the basic chemistry for life might be widespread in the universe. The abundance of organic molecules suggests that the basic chemistry for life might be widespread in the universe. The discovery of these molecules supports the idea that organic compounds could be delivered to nascent planets via comets, asteroids, or interstellar dust, potentially seeding the precursors to life. Sagittarius B2 is also of significant interest to astronomers because it provides insights into the processes of star formation. The cloud is densely packed with regions of active star formation where collapsing gas and dust are giving birth to new stars. The discovery of alcohol and other organic molecules in Sagittarius B2 was made using radio telescopes, which detect the specific frequencies emitted by molecules as they rotate and vibrate. These emissions allow researchers to identify the chemical fingerprints of substances in distant interstellar clouds, even if they are thousands of light-years away. This finding underscores the complexity of interstellar chemistry and highlights the role that molecular clouds play in shaping the chemical landscape of the universe.
Neutron stars are among the most extraordinary and extreme objects in the universe. They are the remnants of massive stars that have undergone a supernova explosion and collapsed under their own gravity. After the explosion, the core of the star is compressed to the point where protons and electrons combine to form neutrons, resulting in an object with an incredibly small radius, typically about 10 to 12 kilometers, but an immense mass, often 1.4 times that of the Sun. This immense compression gives neutron stars their astounding density. To put their density into perspective, a sugar cube-sized amount of neutron star material would weigh about 1 billion tons, equivalent to the combined mass of all humans on Earth. This unimaginable density arises because neutron stars are essentially giant atomic nuclei made almost entirely of neutrons. The atoms are stripped of their electrons, and their nuclei are crushed together, leaving no empty space. This makes neutron stars vastly denser than ordinary matter. The gravitational pull of a neutron star is equally extraordinary. Its gravity is so strong that it can warp space-time around it, significantly affecting nearby objects. For example, if you were to stand on the surface of a neutron star, an impossible feat due to the extreme conditions, you would weigh billions of times more than you do on Earth. Even light cannot escape easily from the gravitational field of a neutron star, and time dilation effects near its surface would be extreme.
First of all, what went through my mind is how stupid am I to picture...
Neutron stars also exhibit remarkable physical phenomena due to their density and rapid rotation. Many neutron stars are observed as pulsars, which emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across space as the neutron star rotates, creating a lighthouse-like effect. Pulsars can rotate astonishingly quickly, with some spinning hundreds of times per second, a rate maintained due to their conservation of angular momentum after the collapse of the parent star. The composition of neutron stars is a subject of ongoing scientific investigation. The outer crust consists of a dense lattice of atomic nuclei and a sea of degenerate electrons, while the inner layers may harbor exotic states of matter, such as superfluid neutrons or quark-gluon plasma, where quarks, the fundamental building blocks of protons and neutrons, exist freely. Studying neutron stars provides invaluable insights into fundamental physics, including the behavior of matter at extreme densities, the nature of strong nuclear forces, and the properties of space-time under intense gravity. Observations of neutron stars, particularly through gravitational waves emitted during their collisions, as in neutron star mergers, have opened new frontiers in understanding the universe's most extreme conditions.
Venus, the second planet from the Sun, holds the title of the hottest planet in the solar system, despite being farther from the Sun than Mercury. This surprising fact is due to Venus's thick atmosphere, which creates a runaway greenhouse effect, trapping immense amounts of heat and causing surface temperatures to soar to an average of about 475 degrees Celsius or 900 degrees Fahrenheit. These temperatures are hot enough to melt lead and are consistent across the planet, day or night, poles or equator. In contrast, Mercury, which is the closest planet to the Sun, lacks a substantial atmosphere to trap heat. While Mercury's daytime surface can reach scorching temperatures of around 430 degrees Celsius or 800 degrees Fahrenheit, its lack of atmospheric insulation allows temperatures to plummet to about minus 180 degrees Celsius or minus 290 degrees Fahrenheit at night. Venus, on the other hand, maintains its blistering heat due to its dense atmosphere, composed of about 96.5% carbon dioxide with traces of nitrogen and clouds of sulfuric acid. Venus's greenhouse effect is driven by its atmospheric composition and extreme pressure, which is about 92 times that of Earth's at sea level. This means standing on Venus would feel like being 900 meters or 3,000 feet underwater on Earth. The thick CO2 atmosphere traps solar energy effectively, allowing heat to build up over time. The thick sulfuric acid clouds further contribute by reflecting sunlight, but this does little to offset the immense heat retained by the greenhouse effect. Another factor contributing to Venus's extreme temperatures is its slow rotation. A day on Venus lasts about 243 Earth days, longer than its year, which is 225 Earth days. This slow rotation results in minimal day-to-night temperature variation, as the thick atmosphere efficiently redistributes heat around the planet. The conditions on Venus have made it a subject of intense scientific study. Venus's past may have been more Earth-like, with evidence suggesting it could have once had oceans and a habitable climate before the runaway greenhouse effect took hold. Understanding Venus's evolution provides critical insights into climate dynamics and helps scientists study the potential for similar scenarios on Earth or exoplanets. Despite its extreme environment, Venus continues to intrigue researchers. Its surface is obscured by thick clouds, but radar mapping missions like NASA's Magellan and the upcoming Veritas mission aim to unveil its geology and history. By studying Venus, we not only learn about our neighboring planet, but also gain perspective on planetary atmospheres, climate change, and the factors that make planets habitable.
The Moon is gradually moving away from Earth at a rate of about 1.5 inches, or 3.8 centimeters per year. This phenomenon is known as lunar recession. This slow drift has significant implications for the Earth-Moon system and is a result of complex gravitational interactions, particularly the tidal forces between the two bodies. The primary driver of this separation is the effect of tidal forces. As the Moon orbits Earth, its gravitational pull creates tidal bulges in Earth's oceans. Because Earth rotates faster than the Moon orbits, these tidal bulges are slightly ahead of the Moon in its orbit. The gravitational interaction between the Moon and these displaced tidal bulges creates a transfer of energy. Earth's rotation slows down slightly due to this interaction, and in response, the Moon gains angular momentum, causing its orbit to expand and move farther away from Earth. This process is extraordinarily gradual, but its effects are cumulative over long periods. The Moon was much closer to Earth when it first formed about 4.5 billion years ago, likely from a giant impact between Earth and a Mars-sized body called Theia. At that time, the Moon may have been as close as 14,000 miles or 22,530 kilometers from Earth, compared to its current average distance of about 238,855 miles or 384,400 kilometers. The recession rate has varied over geological timescales depending on factors such as Earth's rotation and the configuration of continents, which influence the tides. The Moon's recession affects more than just its distance from Earth. It also impacts Earth's rotation. As the Moon moves away, Earth's rotation slows down, lengthening the length of a day. Billions of years ago, a day on Earth may have lasted only 6 hours, compared to the current 24 hours. In the distant future, this process could result in tidal locking, where Earth's rotation period matches the Moon's orbital period, similar to how the Moon is tidally locked to Earth, always showing the same face. The changing Earth-Moon distance also has implications for phenomena such as eclipses. As the Moon moves farther away, its apparent size in the sky decreases. In the far future, it will no longer be large enough to completely cover the Sun during a total solar eclipse, meaning Earth will only experience annular eclipses. The recession rate is measured with high precision using lunar laser ranging experiments. Retro-reflectors left on the Moon by Apollo astronauts and robotic missions reflect laser beams sent from Earth, allowing scientists to measure the Moon's distance with millimeter accuracy. These measurements confirm the Moon's gradual drift and provide critical data for understanding the dynamics of the Earth-Moon system and its evolution over billions of years.
A neutron star is an astronomical marvel, a remnant of a massive star that has undergone a supernova explosion and collapsed under its own gravity. This collapse compacts the star's core to an astonishing density, making neutron stars some of the densest objects in the universe. To put this into perspective, a spoonful of neutron star material, roughly the size of a sugar cube, would weigh more than Mount Everest, around 10 to the power of 15 grams or about 1 billion tons. This unimaginable density arises from the fundamental nature of neutron stars. When a massive star exhausts its nuclear fuel, it can no longer sustain the pressure required to counteract gravity. This results in a catastrophic collapse, during which protons and electrons in the star's core are crushed together to form neutrons. The resulting neutron star is essentially a giant atomic nucleus, with its matter packed so tightly that a single cubic centimeter weighs billions of tons. The extreme density of neutron star matter means that its atoms are no longer in their familiar state. Instead, the electrons are stripped away and the nuclei are squeezed so closely together that the neutrons themselves dominate. The immense pressure overcomes the electrostatic forces that typically keep atoms apart, creating a state of matter far beyond what we encounter on Earth. Scientists hypothesize that the core of a neutron star might even harbor exotic forms of matter, such as hyperons or quark-gluon plasma, where quarks, the fundamental building blocks of protons and neutrons, exist freely. This density is difficult to imagine, but comparisons help illustrate it. For example, the entire human population of Earth, if compressed to the density of a neutron star, would fit into a space smaller than a sugar cube. Such extreme conditions also lead to incredibly strong gravitational fields, with the surface gravity of a neutron star being about 10 to the power of 11 times stronger than Earth's. Any object falling onto the surface would be accelerated to near-light speeds, releasing vast amounts of energy upon impact. The immense density and gravity of neutron stars also create a range of fascinating phenomena. For instance, neutron stars are often observed as pulsars, rapidly rotating objects that emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across the sky as the star rotates, creating periodic signals that can be detected from Earth. Some neutron stars spin at incredible rates, with some rotating hundreds of times per second, due to the conservation of angular momentum during their formation. Studying neutron stars provides invaluable insights into fundamental physics, including the behavior of matter under extreme pressure and density, the limits of nuclear stability, and the nature of gravity. Observations of neutron star mergers, which produce gravitational waves and heavy elements like gold and platinum, further enhance our understanding of these extraordinary objects and their role in the universe's evolution.
A day on Mars, known as a sol, is remarkably similar in length to a day on Earth, lasting approximately 24 hours and 37 minutes. This makes Mars the planet in the solar system with a rotational period most comparable to Earth's. The slight difference of just 37 minutes has significant implications for future human exploration and colonization, as it allows for relatively straightforward adaptation to the Martian day-night cycle. Mars achieves this day length due to its rotation on its axis, which takes about 24 hours, 37 minutes and 22.7 seconds to complete. Like Earth, Mars rotates in a counterclockwise direction, resulting in a day-night cycle that is familiar to humans. This similarity simplifies the planning of human activities on Mars, as it reduces the need for drastic adjustments to biological rhythms compared to other planetary bodies with vastly different day lengths. This small difference in day length, however, accumulates over time, creating challenges for missions operating on both Mars and Earth time. For instance, the teams controlling Mars rovers, such as Perseverance and Curiosity, often synchronize their work schedules with the Martian sol to maximize communication and operational efficiency. This synchronization, known as Mars time, means working slightly later each day by 37 minutes, which can disrupt human circadian rhythms over long periods. Mars's day length is closely tied to its similarities to Earth in terms of axial tilt, which is 25.2 degrees compared to Earth's 23.5 degrees. This tilt causes Mars to have seasons like Earth, though they are longer because of Mars's longer orbital period, which is 687 Earth days. The combination of a familiar day length and a similar tilt makes Mars an appealing target for exploration, as it shares many environmental patterns with Earth, albeit with key differences such as its thinner atmosphere and colder temperatures. Understanding the Martian sol is crucial for planning human and robotic missions. Life support systems, energy generation, especially solar power, and activity schedules must account for this slightly extended day. For potential future colonies, adapting to a 24-hour, 37-minute cycle is considered manageable, especially compared to more drastic adjustments that would be required on planets like Venus, where a day lasts 243 Earth days, or Jupiter, where a day lasts just 10 hours. The close resemblance of a Martian sol to an Earth day is a reminder of Mars's potential as a second home for humanity. This similarity, combined with its proximity and relatively hospitable surface conditions compared to other planets, makes Mars a prime candidate for future exploration, settlement, and possibly even terraforming. It serves as a key focus for current and future space missions, aiming to expand humanity's presence beyond Earth.
Thank you for watching. We hope these mind-blowing facts left you amazed and inspired. Don't forget to like, subscribe and hit that notification bell because there's plenty more where that came from. Stay curious and we'll see you in the next one.